Hello, in this video we are going to see how we can design a circularly polarized antenna for 1.57 GHz, which is mainly used for GPS application on an RT-derived substrate with thickness of 1.575 mm. So our main aim will be how we can find out the length and these cut dimensions, etc. So let's see that. I'm going to use the Pasternak online calculator, and I have put the dielectric constant, the dielectric height and operation frequency, everything. And if I click calculate, it will be getting calculated. So here we can see that these are the length and width. As we are going to design a circularly polarized antenna, both length and width should be the same, and we have to select the resonant length as the dimension. So I'm going to choose this as the dimension. So for the circularly polarized antenna cases, the length of the square has to be little bit less than this value. So we have calculated that value here, and okay, so when we are going to design that for our circularly polarized purposes, I'm going to choose a value which is less than this value. These values I have optimized to get the circular polarization, and this cut is also like I have taken around 10% of this length. So I have taken the 10% of length, which will be around 6.2 mm, and I have optimized it. So these are the optimized values. So the optimization is done using the CST itself. I'm going to use these values for the simulation, and my main purpose is to show you how you can see the circular polarization results like axial ratio and the current, how these right hand circularly polarized field will be rotating, those sort of results. So I'm not showing the optimization. If you want to optimize for any frequencies, you can use design using these calculator, use the length value, and uh, take a value which is slightly less than the length and then optimize this cut value. So this cut value, that is this truncation, is the main parameter which is contributing for the circular polarization. And the probe position is like previously in case of a rectangular patch antenna, where is the probe position comes, that is the same for the circularly polarized antenna also. So that in that case, the probe is, if we are considering this y-axis, it has to be uh, in mid of this position. So maybe I will draw it. So if we are going to consider length here, so this is the mid position. From here it has to be L by 4. So that is this one. And along the x-axis it has to be at the midpoints. That is why the position has to be 0 minus L by 4. That is the feed position. So that is where we are getting the 50 ohm impedance. And this is why I have written here is in order to show you how you can make this cut here. So why I am using this parameter here. So first of all, I'll be drawing a square, and then I'll be using some triangle portion to subtract that from this patch. That is why I have written these parameters here. Okay. And this is the dimension of the coaxial cable, SMA connector that we are going to use. So we have a simulation in our channel to see how these parameters came. And okay, so this is just to show the results. So before going to that, let's do the simulation and see the results. Let's start. Okay, let's start. New template, antennas. So this is a planar antenna, time domain. So our frequency is 1.57. So I'm going to use frequency from 1 to 4.8. So this is the frequency I'm going to use. So next we are going to first design the dielectric. Okay, minus d by, so d is the dimension of the dielectric. And it's on RT Durod substrate RT 5880 Rogers RT lossy 2.2. Okay, the epsilon is 2.2 load. Okay, so the D is 75. Use that value 75. Okay, so next our okay, we didn't provide the height, sorry. So while defining the brick, we have to provide the height. Height is 1.575. Okay, so now we have the dielectric. Okay, so let's check. Height is 1.575. Our next purpose is to provide the ground. So I'm going to draw the ground. It also has the same dimension as the dielectric. Okay, but it is on the bottom plane, so 0 we can put PC. So now we have the ground, and my next step is to draw the patch, which is square patch. Let's name it as patch, and its dimension is L. So it is on the top of the dielectric, and I am going to provide a thickness of 0.035, and it is also PC. So the length, okay, so the length is 62.87. So I'm going to put it as 62.87 here. So now we have the patch. Okay. Okay, so our next purpose is to draw these cuts here. So we know that these are the dimensions for the cuts. So let's do that. So to draw those type of cuts, what we can use is we can use these option, polygon option. So let's do start from here. So because I have to provide a triangle cut here. So we have to provide this x and y values that we know that these are the values. Okay, so let's put these values there. So I'm going to start from here, L by 2, L by 2. So starting from here, so I'm going to put it as L by 2, L by 2, and then I'm going to move along this value. So here the value of y is L by 2, x is L by 2 minus cut. So it is L by 2 minus cut. Cut value is, so what is the value of cut? 6.1. So I'm going to put it as 6.1. Then L by 2 minus cut to L by 2. So we reach here, then we have to go here. So here x value is L by 2, y value is L by 2 minus cut, and then we have to move back to here. So that is also L by 2, L by 2. Okay, so it will be created on the ground plane because we haven't provided any thickness. So it will be created on the 0 z axis. So we have to transform that to top of the ground plane. So it will be on this curve. So click on it, then transform. So we have to transform by the thickness of the dielectric, that is H. So now it reach on it, but still it is a curve. So we have to make that a thick surface. So for that you can use this extrude option. Oh, sorry. Click on this one, then extrude option. Here you can see that return to confirm. Return means enter. So we can provide as truncation, and we can provide it the thickness of 0.035. That is the thickness of PC that I have given. Then the material is also PC. Then click OK. So we have the solid created here. So now what we have to do is we have to mirror this to here also, because we need the cut at this portion also. So let's do that. So this is our truncated position. So we have to mirror, because we need this also here. You can click copy, and as the mirror is along this axis, that is along both X and Y. Let's preview. So here you can see that along this axis it is mirrored. So if you click OK, so we have both trunk and trunk 1 created here. So now our purpose is to subtract this one. So click on it. So if you want to subtract, you can use this Boolean option and subtract, then shrunk. So similarly, you can do the patch Boolean subtract, and then so it is getting subtracted. So now we have the truncated patch, and okay, now we have to provide the feed. So our patch is ready. So for the feed, okay, so for the feed, these are the dimension. So we have the inner conductor, PTFE material, and the outer conductor. R1 is the radius of inner conductor, R2 is the radius of PTFE, and R3 is the radius of PC. So let's design that. So the inner conductor has to come from below to the top of the patch. So let's do that first. So this is the inner conductor. Inner conductor. It has a radius of R1 and X center and Y center. So X center and Y center, because that is the feed position. So this feed position is 0 minus L by 4. So we can give it as X center 0, Y center minus L by 4. And Z minimum, so it has to be come from down to the top of the patch, that is H plus 0.035, and it is PC. So let's see. So R1 we are giving it as 0.45, and H minimum I'm going to give it as minus 6. So here you can see that it is coming from minus 6 to top of the patch. Okay. So our next step is to uh, design the PTFE. So let's PTFE. So it has an inner radius of R1 and outer radius of R2. X center and Y center is minus L by 4. So it has to come from H min to 0, that is up to the ground plane. So this material is PTFE. So we can go for PTFE. Okay, load. So R2 is 1.5. Okay, it is PTFE in. intersect with ground. Okay, so let's do it as okay, because we can remove some portion, because now this is intersecting with the PEC plane. So now we can remove some portion, because here you can see that this inner conductor is in short with the ground. So now let's do that, because we have to remove some portion from here. So for that, again click that one. So this one has to be subtracted. So it has an inner radius from 0 to R3 minus 0.1. R3 is the radius of the outer conductor. Okay. Then X center and Y center is minus L by 4. Z minimum and Z maximum are 0. So it has to be PC. Okay. So R3 is 1.9. So now we have that one created. Now we are going to remove that from ground. So we have some portion. So now our aim is to provide the outer conductor. So it has a radius from R2 to R3. Y center is minus L by 4. Z minimum is from H min to 0. So this is PEC. So now we can see that it is getting connected to the ground plane. So the inner conductor is shorted to the top patch and outer conductor is connected to the ground plane. So I think everything is ready. Okay. So now what we have to do is, because if we want to find out this uh, antenna is working as a CP, what we have to do is we have to check the axial ratio. So for that we need to check the far field. So you can go to field monitors, new field monitors, and you can go to far field and transient broadband. So this means that from 1 to 4.8 gigahertz it will be split into 21 frequencies and every far field will be calculated. So this is how the field monitor has to be set. Next we can see how you can set the axial ratio. So you can go to post processing, result template, and far field antenna properties. Here you can get for far field result. So far field result, so it will show this thing. So you can go to directivity constant phi equal to 0, then click all settings. So it will open this thing. So because we have set the broadband far field, check this thing, and we are going to check the far field in the single direction where theta and phi are 0, that is on the broadside direction we are going to check the value. So theta and phi are 0 broadband, and it will be taking the far field result from the navigation tree, and you can select directivity or gain, whatever is okay, and you can check the axial ratio here, then okay. So this is going to show you the axial ratio. I'm going to rename it as axial ratio because we are calculating the axial ratio here. Okay. Okay. So now we have set far field and axial ratio. And before going, you can check the mesh settings. If you can increase the mesh settings, that is okay. I may have to decrease the mesh setting because I'm using the learning edition and it has some limitations. And make sure that the background is normal, that is it has an epsilon of 1 and mu of 1, and the boundaries are lambda by 4, open boundary condition of lambda by 4. So now everything is set. I think everything is okay. Then you can run. No, oh, so sorry, we didn't provided the port, so we have to set the port. So you have to select the phase. So if you click F, you can select the face. Otherwise, you can go to fix, and you can use pick face option. So I'm going to select this face and I'm going to click new waveguide port here. So here you can see that port is created and this arrow is going into the patch. So click OK. So now we have the waveguide port. So now you can click and start the simulation.